So special derivatives, implicit differentiation, related rates. It's really just 3 lectures spread over 4 days. Today we're going to do some special derivatives, and we're going to introduce implicit differentiation. Next class we are going to do lots of implicit differentiation, and that's it. Then the following class we'll finish up implicit differentiation, and we will introduce related rates. And then in the last class we will only do related rates. The first topic on special derivatives, not too important, but moving forward into this test for this unit, there'll be a couple questions on this stuff, and it's pretty much you know it or you don't. The big stuff is on implicit differentiation and related rates. Related rates is your first experience of like application of derivatives and rates of change, and you get some word problems, and you talk about, you know, the instantaneous change in a specific thing relative to time, and it starts to get more difficult, more challenging. I'm going to be interested to see how you guys do and how I do the first time, and whether my problems are too hard or maybe I need to spend more time on related rates. We'll figure it out. Probably the review day will be spent just going over related rates. What's up, Mr. Wood? I'm sorry. You're not the biggest guinea pigs of them all. That's the first period that I teach. That's period 2. I change like the way I introduce things. Yeah. And I'll change like the quizzes a little bit. Like I'll change, whenever I say change this to that, it's because first period. Yeah. Because, yeah. Well, first period's really smart, so they've been able to adjust and adapt. So. Said first period's really smart. They've been able to adjust and adapt. No, it's just they're doing good. All right. Yeah. So we know pretty much every single derivative rule. Put the shirt down, Miss Elliott. Except for a couple of functions. They have their own special rules. Functions like e to the x or some number to the x. A stands for just a number, some constant. The natural log of x and the absolute value of x. Okay, these are all different functions, and we don't know how to take the derivatives of them, but we'll find out today. And surprisingly, they're all kind of similar. Close. First, let's talk about e to the x. Do we know what e is? Anybody know what e is? It's a, what was it, natural? Yes. It is a constant. It is like 2.71 actually, not 2.93. Okay, so e is a constant. You can treat it like pi. It's not a variable. Does anybody know how you can calculate e? In that situation, Ms. Vaughn, it's a variable. So in that situation, it stands for energy. It does not stand for the mathematical constant. It is actually the limit, and you guys know limits now, so you can kind of understand that. As x approaches infinity, of 1 plus 1 over x to the x. Okay? You guys kind of understand?
Are we going to know
Uh,
Should I write it down? Should I write memorize?
no. But it's just interesting. You know, and really it was developed, it's used a lot in finance, continuous compounding. Well, mathematicians kind of formulated the number by kind of evaluating certain situations. So like 1 plus 1 divided by, let's pick out 10,000 to the 10,000. we can see 2.718, that's getting closer to what E's true value is. So we continue to put in numbers bigger and bigger and bigger, and we approach a specific number, E. And mathematicians decided, just like they decided pi was pi, they decided E was the number E. So that's good. It's important to know that E is just not a variable. All right, so we know that probably exponents and logarithms are related. They're actually inverses of each other. Okay, so we can use logarithms to solve equations with exponents. We can use exponents to solve equations with logarithms. But let's talk about the derivatives. Derivatives are interesting, and we could kind of like explore this function and look at, you know, the instantaneous change, or I could just tell you what the derivatives are. So I'm just going to tell you what the derivatives are. Both of these are when x is in the exponent form. Interesting, the derivative of e to the x is just e to the x. It's the exact same thing. You want to find the instantaneous slope of e to the x, you just find the function value at whatever point you want to know. What's the slope of e to the x when x is 2? It's e to the 2. Okay? Now, changing this to some number to the x, well, it kind of changes the growth a little bit, the steepness of our exponential growth. So to account for that, the derivative is similar to the e to the x. It is a to the x. But to account for this little change, you multiply by the natural log of whatever number that is. Okay? So that's exponents. Let's talk about logarithms or natural logarithms. We'll talk about other base logarithms in a little bit. The derivative of the natural log of x is just 1 over x. Now, some things we have to know about natural log function and the e function. Being inverses of each other, if we look at e to the x and we look at log x, who can describe to me what they would look like? How they would be related? Here, let me just delete this. This is e to the x right here. Exponential growth. What does log x look like? No. Exponential decay would be like that. That would be kind of like a reflection over the y-axis. Beautiful. Inverse functions are reflected over y equals x. You know how when you were finding inverse functions, when you were taking algebra 2, you took your y's and x's and flipped them, and then you solved for y to find your inverse? That's kind of what it is. You're taking your y's and x's and flipping them. So when we graph log x, where is it? Log x. No, that was apps. We will see a reflection over a y equals x. And there it is. Now, what do you notice about the graph of log x? Beautiful. The function is not defined when x is less than 0. It is, or equal to 0. E to the x will never approach 0, so we can never plug in 0 to log of x. So what we say is, in this situation, x must be bigger than 0. But we'll look in a little bit how, if we take the absolute value of this x, we can take the derivative of that for any x. And that leads us to our last one, the absolute value of x. The derivative is interesting. It's just x, or sorry, 1. No, it's x over absolute x times 1. Okay, we looked at this function when we were talking about limits. It's one of those piecewise functions where it's a constant value to the right of 0, that's 1, and it's -1 to the left of 0. If we look at the graph of absolute x, it's a v. To the right of 0, we have 1, the slope, and to the left of 0, we have a slope of -1. So that produces that. Okay, cool. So those are simple. Now, instead of having just an x, we could have a function. Okay, so e to f of x. Mr. Witt, you're really going to mess me up if you keep doing that. Can you just sit in your seat regularly? We could have a to a function. We could have the natural log of a function. We could take the absolute value of a function. Hi.
Megan?
Good luck, Megan.
Oh, I didn't play. You told me I couldn't get it.
Okay. Later. So we're going to have to use the chain rule. Okay, chain rule is take the derivative of the outside, leave the inside, then take the derivative of the inside. Well, in this situation, e is considered our outside function. So what we do is like we pretend f of x is like a big X. Well, the derivative of e to the x is just e to the x. So using the chain rule, we have e to the x. Instead of this red x, I put f of x times the derivative of this inside piece. Even though this is an exponent, this is considered the inside. The derivative of the inside would be f prime of x. So it's really just e to the same thing times the derivative of that. Okay, if we have a number to an exponent, it's going to be the same thing as this, only we're going to multiply it by the derivative of what's up here. So we will have a to the x log a times the derivative of the inside piece. In this situation, the inside piece is that f of x. So notice we're just kind of adding one little thing using the chain rule. That's what the chain rule is. That's an a to the f of x ln a times f prime of x.
I thought for the chain rule that f of x is the outside.
I mean, I could have put this as g of x. You know how we usually said for the chain rule it's f of g of x? Yeah, and it's really just take the outside, take the derivative of the outside, leave the inside. No, in this situation, since it's in an exponent, the e is the outside. Okay, it's not like e squared. That's just a constant. E is a number to a power, the x's are up here. E to this power would be the outside. This function up here would be the inside. Okay? So here, the natural log, that's the outside. You got to see how this is the outside, right? Okay. It's just a little difficult with the exponents. It's just new to see. So if we took the derivative of this using the chain rule, it's the derivative of the outside, which would be 1 over, this would be where our big red x is. So the derivative of log x is 1 over x. Since it's f of x, we leave f of x, and then we multiply it by the derivative of the inside. Chain rule. That's the derivative of that inside f of x. And finally, you guys could probably do this. It would just be f of x over absolute value of f of x times the derivative of f of x. All chain rule. Just what you saw for those original derivatives multiplied by the derivative of whatever you have in your exponent or in your log or in your absolute value. Okay? Any questions? We kind of have to commit these to memory. So, yes, put memorize next to those. But really, as long as you memorize these four, these should not be as difficult if you just understand the chain rule. Can I go down? Yes. All right, let's do a couple practice problems. Do you need that a little more? Sorry. We good? Okay. Find the derivative of some absolute value functions. Well, the derivative of absolute value of x you guys have is x over absolute x. Well, the derivative of a function like this, the absolute value of x squared minus 4, that would be the function, I would say f prime of x is equal to the function divided by the absolute value of the function times the derivative of the function, or the derivative of the inside part, not really of the entire. Okay? Cool? Well, now that you really know how to do all derivatives, you can take a derivative like this. We have an absolute value function. We have a chain rule problem on the inside where we have three functions. We have a big X cubed, we have the cosine of an x, and we have 2x minus 1. So give it a shot, check with a neighbor. Let's do some work today. Especially those of you who struggled. The second one is a good chain rule problem. To make sure you understand, you know how to do. Okay? Times the derivative of the next piece times the derivative of the last piece. Just like a chain rule problem. You're taking the derivative of cos cubed of 2x minus 1. Just be 2. Whew. Check your answers with a neighbor. See, most of you are good to go. Some of you aren't going far enough with your chain rule. Some of you are good. Whoa. Great. There is our derivative. Derivative of cos cubed of 2x minus 1 is 3 cos squared of 2x minus 1 times the negative of sine of 2x minus 1 times 2. So I could kind of combine the cos of 2x minus 1s. I have 5 of them. This is a 5. Multiply by the sine, combine the 3 and the 2. This would be simplified. But again, this is simplified. Good. All right. Any questions? You had a question? Anybody? I feel like we were all doing pretty well on that. So we already talked about what E was. Let's just do the derivative of these couple. What is it, Mr. King? What's the derivative of e to the 2x? E2x, is that it? Times the derivative of what we consider our inside piece, which is 2x. Okay, so f prime of x is equal to 2 e to the 2x. Before we do this one, what is the derivative of e to the negative x? Mr. Bewley, what is it? Yes, e to the negative x times negative 1. Or negative e to the negative x. Okay? I'm sure I heard that from a lot of you. So let's do this one. For this one, the x cubed is the outside function. Then we have the derivative of the inside to worry about. Okay? My first is take the derivative of my big red x cubed. That's 3 big red x squared times the quantity, which is the derivative of the inside. We talked about the derivative of e to the negative x being negative e to the negative x. And we've talked about the derivative of e to the x is just e to the x. Okay? That's it. Cool. All right, let's do a couple more. So 5, now we have a constant to a power. So that's when we talk about that a to the x, the derivative being a to the x log a. Here we have 5 to a function. So go ahead and take the derivative of that. It's just like e, only you're multiplying by the log of that base value. Okay, if you look up at the original derivative of a to the x, it's a to the x log a, not log x. So it's a to the x log a. So when we take the derivative, it would be 5 to the big X log 5. Using the chain rule, find the derivative of that big X.
Would you not go further than that?
Mm-mm.
I know. Why would you go further than
What's the derivative of 3x squared
Oh.
plus 2x minus 5? You don't have to use the chain rule with that,
Okay.
with that piece. Okay, and this guy, go ahead and try that guy out. going to start using dy dx a little bit more. You'll see why moving forward. So be comfortable seeing this, that being the derivative or the instantaneous change in y over the instantaneous change in x. We have the same thing, log 2 times negative e to the negative x. I wouldn't put that negative in front of the 2, e to the negative x. It has to be like in parentheses and then in front of that, because we have to use the order of operations there. So you can change it to a -1 maybe, and do -1 times that, whatever. But that's it. Any questions on that? Pretty straightforward once we get the hang of it. You could be asked questions like this. Find the xy location of the horizontal tangent to f of x equals x e to the x. So what do we have to do? I don't know. There, let's do something. I do this with my algebra students. Mr. Valdez, pick a number between 1 and 5.
3.
Pick a number between 1 and 6.
4.
Pick another number. Okay, it's probably hard. You're up. What do I have to do to solve this problem? Yeah. Location. Columns, rows, whatever, Miss Elliott. Okay. Yeah. What do you think? What do I have to do? Yeah. Let's find the derivative first. What do I have to use to find this derivative? The what rule?
E to the x rule.
E to the x rule and? Yes, the product rule. Putting you on the spot. Okay. So f prime. This is my f. This is my g. F prime is 1 g plus, what's the derivative of e to the x? E to the x. G prime times f. All right, that's the derivative, and what do I have to do with that derivative? That's probably our. Yes, set it equal to 0. That's what it means to be a horizontal tangent. Your slope is 0. All right, now we have to solve. I'll open this up to the floor. Any ideas on how we can solve this? Beautiful, Mr. Shameen. Let's factor out a e to the x. He just enjoys these lectures. I'm glad. Not everybody does. Right, Mr. Brooks? Right. Right. All right. Mr. Perkins, do you have a question? All right. I found the derivative function, which is this, and then I just set it equal to 0. So like, oh, no. I tried to say this is my f, that's my g. Sorry. Yeah, my bad. Okay, so we factored out an e to the x. So really we're trying to figure out when does e to the x equal 0 and when does 1 plus x equal 0. Oh.
For the x prime, isn't it e to the x plus e to the x times 1? Because it's the x.
G prime f. This is
Okay.
f prime g, derivative of f is 1, g, plus g prime, this is actually the derivative of g, times f.
Oh, okay.
Got it? Product rule. Just we have like repeated things with the product rule because the derivative of e to the x is e to the x. All right, so I factored it out. I know that definitely x is -1, but what about this piece? When is this equal to 0? True. Never. If I picked 0, if x is 0, what's e to the 0?
1.
Yeah, e to the 0 is 1. What's e to like the negative fifth power. Is it a big number or a small number? It's close to 0. Okay, as we continue to put in bigger x values, positive, this gets huge. As we continue to put in bigger x values that are negative, this gets closer to 0. So e to the negative infinity approaches 0. That's e to the negative infinity. Approaches 0, but it never gets to 0. So I won't put it equals, I'll say approaches. All right, so this is it. Now, on your test, there was a problem that asked you for the points where we had horizontal tangents. And a lot of you just gave me the x-coordinates. And I should have been strict with you guys. And I wasn't. But in the future, I will be. Let's find that one. This one was not it. This one. 25. Asked you for the points where f has a horizontal tangent line. You would have gotten x is equal plus or minus 2 as your x-coordinates. And a lot of you gave me this as your answer, and I marked it correct. I probably should have taken off something because you didn't follow directions. And in the future, I will. So here's your heads up for that. If I ask you for points, I want points. And if I ask you for x-coordinates, I want x-coordinates. So I was nice with that. So we know x is -1. I will plug in -1 into my function to find f of -1. That'll be negative e to the -1. And that's it. Your point would be -1 comma negative e to the -1. And you can rewrite this as -1 over e if you want to, because that's the same as e to the -1. That's your answer. All right. Now, moving into finding the derivative of log functions, we need to review some log properties. So, some ones that you probably remember. If we're taking the log of two things being multiplied, does anybody remember what you could rewrite that as? And you did this in pre-calc, you did this in algebra 2. The log, the natural log, or any log of x times y is equal to what? Did you say what in between, Mr. Shameen? Yep, that's correct. So you have two things being multiplied inside a logarithm. You could take the log of both of those individual things and add them together. Logs being inverses of exponents. Exponents have interesting rules combining exponents. Logs have interesting rules as well. So we can divide two things. And that would be like subtracting the natural logs of both of those. We could take x or anything to a power. What happens with this power? Mr. Valdez? Yeah, it goes down in front. Okay, those are three important ones. A couple other just like you should knows. If I'm taking the natural log of e to the x can go down in front. The natural log of e is just 1, so this is just x. And kind of almost conversely, e to the natural log of x, since they're inverses of each other, they undo each other. This is just x as well. Some important things, you can't take the natural log of 0. However, the natural log of 1 is 0. And the natural log of e is just 1. Okay, these we kind of have to remember if we don't know them already. What this is saying right here, if I took e to both sides, it would be like 1 is equal to e to the 0 power. Okay, so natural log of 1 equals 0 is like saying 1 is e to the 0 power. All right. Well, let's take the derivative of q of x, which is equal to the natural log of x to the 4th. We could either use our properties that we know to take the derivative of this, or we can use the chain rule and kind of use the derivatives that we talked about, kind of those formulas at the beginning of the lecture. So let's first use properties and see if I can simplify the natural log of x to the 4th. What can I do to make this maybe different? Put the 4 in front. What's the derivative of 4 ln x? Beautiful. The derivative of a constant times this is just a constant times the derivative of this. The derivative of log x is 1 over x. So we have 4 over x. Cool. So that's using the properties. Help you simplify something and then take the derivative. We could use the chain rule. Sometimes we aren't easily able to simplify, and we'll have to use the chain rule. So the chain rule says if we take the derivative, we pretend this x to the 4th is like a big X. That's my outside function. The derivative of my outside is 1 over x, but the big X is x to the 4th, times the derivative of my inside, 4x cubed. Well, I can simplify that. I have 4x cubed over 4x to the 4th. X to the 4th, not 4x to the 4th. And that's equal to 4 over x. So either way, you get the same answer. It's up to you what you want to use and how you want to use it. Sometimes you're going to really, really want to use log properties instead of using the chain rule. Example are these two. I could say the derivative of this h of x is 1 over this function times the derivative of this function. Right? No problem. That's fine. However, I would rather rewrite this function using my log properties and take the derivative of that. Now we just have two separate pieces. We don't have to worry about any quotient rules or anything crazy. The derivative of my first piece is just 1 over x minus the derivative of my second piece. That's 1 over what I have on the inside times the derivative of the inside. Cool. It's really a lot easier than using the quotient rule to find the derivative of x over x squared plus 1. And having like, I mean, it's not maybe that much easier. I just think it's a little easier. For this one, this would be a mess and a half. You have chain rule, you have product rule, and you have quotient rule all in one function. I would not ask you to take the derivative of this as you see it. You could, but that would be cruel. Instead, I would ask you to rewrite this function using your log properties. And you're probably like, well, Mr. Messer, we still have some chain rule. It's still kind of messy. What can I do with this 2? What can I do with this 1/2? I can bring it down in front of my logs, making this nice and easy. This will be ln x plus 2 ln of x squared plus 1 minus 1/2 ln of 2x cubed minus 1. Okay, I'm not going to take the derivative of that, just showing you how, really, when you were taking Algebra 2 and pre-calculus and we were doing all these log properties and you were asked to expand problems like this, it was for this purpose, so that you could take the derivative of that easily. Really, there was no other purpose that you guys were going for. You weren't like solving equations with this, you were just like expanding this and you got this and you put this down as your answer and you got a check for getting it right. The reason why you learned how to do that is because it helps you take derivatives. So there's always a purpose in your math classes. Sometimes. Mostly. We'll say that. Mostly. One more log property I forgot to mention. If you have the log of some x of some y, log base x of some y, you can use the change of base formula to rewrite that as the natural log of y divided by the natural log of x. That's an important one. So write that down. Because when we deal with logarithms with different bases besides base e, like this, we are going to want to rewrite this as ln of x squared plus 5 divided by ln of 3. And then we'll take the derivative. We should know that ln of 3 is not a variable. We don't have to use the quotient rule here. It's just a constant. So when I take the derivative, I can just leave it out in front as a constant. Take the derivative of my numerator, and I get that. 1 over my function times the derivative of my function. Any questions? Comments, concerns? Well, let's look at the derivatives of the natural log of the absolute value of f of x. All right? We know that the derivative of absolute value of f of x is what? Mr. Brooks, could you tell me? Yeah, absolute value of x. See, he's got it in his head. You don't need your stinking paper. Good. Okay. So, we're going to take the natural log of this. This is what's going to happen. And you can write this down if you want to. It'll be 1 over absolute value of f of x times this. The derivative of the inside. The outside is natural log. The inside is absolute value of f of x. So I'm going to multiply it by this, the derivative of my inside, which is f of x over absolute f of x times f prime of x. Okay? That's messy, right? Well, it gets simpler. Absolute of f of x times absolute of f of x is equivalent to what? Beautiful. F of x squared. So I can rewrite this as f of x over f of x squared times f prime of x. And what happens now? Yes, this f of x cancels with one of these f of x's. And it turns out the natural log of the absolute of f of x turns out to be the same thing as the derivative of the natural log of f of x. The absolute doesn't make it any more complicated. It is just, and I'll clear out some space here, 1 over f of x times f prime of x. That comes from here. We'll go over here. The derivative is 1 over f of x times f prime of x. Okay, so we don't have to worry about the absolute values when we see them. So if I ask you to take the derivative of the natural log of the absolute value of sine of x, you're not going to freak out because you see the absolute value. You know they end up just like canceling with one of your functions when you're doing all this crazy stuff. And you just say, well, Mr. Messner, that's just 1 over sine x times the derivative of sine x. And what is that? Cotangent x. When we go backwards with integration, we'll be asked to integrate cotangent of x, and we will have to figure out that the integral of cotangent x is the natural log of the absolute value of sine of x. We go backwards eventually. It's going to be fun. Integration. Here, natural log of the derivative of the natural log of the absolute value of cosecant of x is 1 over the cosecant times the derivative of cosecant. Which is interesting because you end up with just negative cotangent of x. Questions? Okay, these rules, once we get the hang of them, and you'll practice them for homework and we'll quiz on them, are not that bad, but you have to be familiar with them and you have to be comfortable working with them. So let's go into implicit differentiation. I told you we're going to intro implicit differentiation. It's just an intro, and then we'll just stop. I believe there's a couple of questions on implicit differentiation, but maybe not. I'm not sure. All right. No. We got 15 minutes. We're almost there. I'm driving 13 hours to Atlanta over Christmas break, and I'm going to have to wait longer than deserved.
Yeah, you can stop at a gas station. Technically, I don't even have to ask.
I wait for gas stations. Gas stations. So like every 3 hours, I'm holding it. Go ahead, Mr. Witt. If it's going to be freaking classroom led by Miss Sloan versus teacher, I guess I'll stand down and let you go to the bathroom. All right. So typically our equations have been in explicit form. Explicit equation. Y is a function of x. Explicit means stuff is implied. It's easy to work with. I can look up the definition of explicit. It says stated clearly and in detail. No room for confusion. Y is equal to x's being manipulated. Simple. Functions are an explicit form. Okay? Not all equations can be written explicitly. This is not a function. What? Probably get really good Wi-Fi in here. I think I'm hardwired in to the network. And I believe you can still just barely get faster speeds hardwired in than over the air. But I think it's getting closer and closer every single year. So explicit, stated clearly. Implicit, an implicit function is implied though not plainly expressed. Okay? An implied function. This is an implicit equation. This is not a function. What is this equation? What will this equation produce a graph of? A circle, correct. Circles are not functions. It's a circle with a radius of 3. What? Half a circle? No, it'll be a full circle. Yeah, we got to do the plus and the minus when you take the square root of both sides. That's a full circle. This is a full circle. It definitely is. Trust me. If you solve for y, you plugged it into your calculator, Mr. Brooks, you have to plug in both. Y is equal to positive square root of 9 minus x squared. Let me just show Mr. Brooks here. Are you sure? I'm positive. All right. Yes, you can't plug it in like the x's and the y's in there. Here's our circle. Yeah. You do this not going to Mr. Marquez. You gotta teach or give blood. All right, so let's talk about getting derivatives. Now, how do we take derivatives? Well, what we do, and we don't really show this step, write this down, is we take the instantaneous change with respect to x of both sides of my equation. And we never show this because we always jump to, okay, 2x plus 2. Okay? But the proper steps is take the derivative of the left side, take the derivative of the right side with respect to x. Now, usually we always jump to the derivative of this, right? 2x plus 2. And Mr. Messner always, on your quizzes, says y prime equals, or f prime of x equals, or dy dx equals, because you can't forget that we have a statement, an equation. So here, the derivative with respect to x of y is dy dx, the instantaneous change of y with respect to x. Okay, what were we finding when we took the derivative? We were finding dy dx, or y prime, or if it was a function f of x, f prime of x. Well, can we do the same with our implicit equation? That's the million-dollar question. Can we take the derivative of this? Well, let's see. We would do the same thing. We'd take the derivative of the left side and we'd take the derivative of the right side, right? When we have two things being added together, we're taking the derivative of those things. We take the derivative of the pieces, right? And I didn't show that up here, but I'll show it down here. Take the derivative of x squared, the derivative of 2x, the derivative of 3. So the derivative of x squared plus the derivative of y squared is equal to the derivative of 9. All right, let's start breaking it down. Let's start with the derivative of x squared. 2x, good. We haven't gotten everything. We'll skip this part. We'll come back to it. Don't worry. We'll see. What's the derivative of 9? 0. All right, let's talk about the derivative of y squared. Let's first talk about what the derivative of y is. What did we say in our previous equation? What was the derivative of y? Right? We said it was y prime, or dy dx. We just assumed that it's just the same thing with a prime. Okay, well that's correct. The derivative of y is dy dx, or y prime. Okay? Well, let's treat this as a chain rule problem. Let's put parentheses around y and treat that as like a big red X. Okay? What's the derivative of that big red X squared? 2x, right? But instead of the big red X, we put what? Y. So we got 2y times the derivative of my inside. The derivative of the inside, which is the derivative of y, is dy dx. So it turns out the derivative of y squared is not 2y. The derivative with respect to x of y squared is 2y dy dx. I know, trust me, it'll get more annoying and more complicated. Isn't that just what? Well, we're not done yet, technically. What we're trying to find is dy dx. What we are finding here is what dy dx is equal to. We're going to do the same thing here. We need to find dy dx. How do I find what dy dx is equal to? Solve for it. Thank you, Ms. Smith. How do I solve for dy dx? What should I do first, Ms. Smith? Subtract 2x from both sides. I get 2y dy dx is equal to negative 2x. Now what do we do now? Divide by 2y. Turns out, since our original equation was not a function, we're not going to be able to express the derivative as a function in terms of just x's. We have to express the derivative as a function of both x's and y's. And this is the derivative of that circle. Good intro. All right, take a 3-minute mental break. Next class, we're going to do a lot more of those. 3-minute mental breaks. What? Like negatives and assuming you saw the answer and sure.
And then
Talk about this like what you got wrong?
yeah.
Okay.
I think someone didn't have it quite.
Okay, sounds good. I'll keep it on the top.
And the notes are online.
Yeah, the video will be online.